previous mathematics courses, you have studied a variety of graphs and their important characteristics. In this section of your assignment, you will be comparing the characteristics of an exponential function and a logarithmic function. As you are comparing the two graphs, here are some characteristics you should consider. Domain and range. The domain is the set of all possible input values, and the range is the set of all possible output values. Intervals, where the function is increasing and decreasing. Maximums and or minimums. X and y intercepts. Growth of the function from left to right. And asymptotes, a line such that the distance between the graph and the line continually approaches zero. For example, here are a list of characteristics for the graph of f of x equals x squared. The domain is negative infinity to infinity. The range is 0 to infinity. The minimum is at 0, 0. The x-intercept and y-intercept are also at 0, 0. The graph is decreasing from negative infinity to 0 and increasing from 0 to infinity, and there are no asymptotes. In the task you did today in class, Powerful Tens, you used the definition of a logarithm and your understanding of graphs to help you in solving logarithms base 10. In this section of your assignment, you will be learning and practicing a new method of solving logarithms. Remember that a logarithm is a function. Just as we can square an expression, multiply it by something, or take a cube root of it, we can also take the logarithm of it. Also remember that logarithms are the inverse of exponentials. Therefore, to solve an exponential equation, we can use logarithms. That is what we will be doing in this section of the assignment. In a previous class, you learned the log of a power rule, which is log base b of x raised to the k equals k times log base b of x. What happens when b equals x? Well, since log base x of x equals 1, then we have log base x of x to the k equals k times log base x of x, which is equal to k times 1, so the answer is k. So, log base x of x raised to the k equals k. Using this principle, you can take the logarithm of an exponential equation to help you solve it. Notice that this only holds true when the base of the logarithm matches the base of the exponent. For example, solve the following equations by taking the logarithm of both sides of the equation. For our first equation, we have 10 raised to the n equals 9.5. Since this is not a simple exponential equation that we know the answer to, we need to use a logarithm to help us solve for n. We can use the principle above, log base x of x to the k equals k, to help us get n alone on the left side of the equation. Since the base of the exponential equation is 10, then the base of our logarithm also needs to be 10. So, log base 10 of 10 raised to the n equals log base 10 of 9.5. Remember that to keep our equation balanced, we need to take a logarithm of both sides of the equation. On the left side, we know that log base 10 of 10 raised to the n equals n, so now we have n equals log base 10 of 9.5. We can enter the right side of the equation into our calculators to get the answer. N equals log base 10 of 9.5 equals 0.9777. Because log base 10 is common, we usually don't write the base, so log base 10 of x becomes just log of x. In this example, the base was included so we could see what was happening. In the next example, the base 10 will not be written for convenience purposes. In our second equation, 10 raised to the x equals 587. Just as in the previous example, we need to take a logarithm of both sides in order to solve for x. So, log of 10 to the x equals log of 587. Since log of 10 to the x equals x, we now have x equals log of 587. We enter this into our calculator to get the answer. X equals log of 587 equals 2.7686. Previously, we have used the formula for compound interest to determine the amount of money in an account after so many years. In this section, you will again practice how to use this equation to help you determine the effect that different compounding periods will have on the amount of money in an account. Here's the formula for compound interest. If P dollars are deposited in an account paying an annual rate of interest R, compounded or paid n times per year, the account will contain A amount equals P times 1 plus R over N, all raised to N times T dollars at the end of T years. For example, how much money will there be in an account at the end of 5 years if $2,000 is deposited at 12% annual interest compounded quarterly? Remember that quarterly means the money is compounded 4 times a year, so we know that n equals 4. Since the initial amount put in the account is $2,000, then P equals 2,000. The amount of time the money is in the account is 5 years, so T equals 5. Since the interest rate is given as 12%, we need to convert this number to a decimal and let R equal 0.12. Now all we need to do is put each of these numbers into our equation to find the amount of money after 5 years. So A equals P times 1 plus R over N to the N times T equals 2,000 times 1 plus 0.12 over 4 raised to 4 times 5, which is equal to 2,000 times 1 plus 0.03 raised to the power of 20, which gives us 2,000 times 1.03 raised to the power of 20, which equals 2,000 times 1.8061, or simplified, $3,612.22. So the amount of money in the account after 5 years is $3,612.22. Notice the order of operations followed in solving the equation above. Make sure that you follow the right order, otherwise your answer may not come out correctly.